Hey Mustangs, in this video we're going to be reviewing chi-square and see how it applies to genetics. Now remember, chi-square isn't just used in genetics, it can be used in any experiment. So the background information for chi-square, you have to understand what is going on, why things are being done in biology to really get what's going on in AP biology. So if you understand the background information and you understand why something is happening, why things are being used, it helps with understanding. So with chi-square can be used in any experiment and of course in genetics as well. So when we look at chi-square, let's say you get results of an experiment and you see here's the average miles per gallon. This is in this case seeing if the back end of the tailgate basically of a truck, what happens if you leave it in a certain position, how that affects gas mileage, and you get these numbers here. And you might be looking at it and thinking, all right, is this significant from 2 gallons different? Is that a significant difference? Can we actually say that the positioning of the tailgate really does make a difference? Or is it, is it not that big of a deal? Are these numbers really not showing that big of a difference? So you can use chi-square to see if your results of what you got from an experiment can be used, should be accepted, or should they be basically rejected. So that's basically what the whole purpose of chi-square is. Are these good enough? Is there a big enough difference that you can either support or reject your hypothesis, whatever it is that you're claiming? So basically you can think of it this way. Is the difference in your observed results due to random chance and are acceptable results, or is there some other factor influencing the results and they should be rejected? That should be a parenthesis there. Okay. So depending on what the outcome is of the chi-square, it could basically, you could finally decide, yeah, the numbers are a little bit off from what I would expect, but they are acceptable, they're close enough, and it's good data, it's good numbers, and my hypothesis is supported. Whereas if the numbers are too different, have deviated too much, then chi-square can help actually analyze that and see if the data and your hypothesis should be rejected, that there's something else influencing. It's not what your hypothesis predicted. All right, so in order to do chi-square, you have to know the formula for chi-square that we see here. So this is the symbol for chi-square, and then the sum of all the observed minus expected squared divided by expected. And then here, this chart, this is the one I gave you in class. This is the one you should be able to use for the AP exam. This one is a lot more detailed, and we basically learned that this line right here, if the number, here's the P05 value, if the number is 3.84, if we're talking about 1 degree of freedom, if it's 3.84 or 6.64, anything bigger than 3.84 here going this way, then we'd say that there's a significant difference and you would reject your hypothesis. Whereas if it's lower than the 3.84, if it's this way, then you would support your hypothesis, or the data supported your hypothesis. So what you see on the AP exam, what they give you is a chi-square table like this. So they give you the 0.05 and then 0.01 to show you that it's increasing this way. So if it's this number here, this number, all these numbers that you see here, depending on the degrees of freedom. So here we're looking at 1 degree of freedom, 2 degree of freedom, 3 degree of freedom. If it's this number or bigger, then that means you should reject it. You should reject the hypothesis. So let's go ahead and take a look and do a couple examples. So in peas, smooth seeds are dominant to wrinkled seeds. In the pea generation, a purebred smooth plant is crossed with a plant with wrinkled seeds. The resulting F1 plants are then crossed. The seeds observed of the F2 generation were, so we're not looking at the parental generation, we're not looking at the F1, we're looking at the results of the F1, which is the F2. So if we take a look at this, basically we would expect if you crossed a smooth purebred, so let's say we're talking about, I'm going to use D because I don't want to use S and I don't want to use W or either of those because it would just throw us off. I don't want us to get thrown off just by the letters. So I'm just going to use capital D. So capital D will equal the smooth, lowercase d will equal wrinkled, and we know that in the parental generation, the starting generation that we're starting from, that there was one smooth plant and it's crossed with a wrinkled plant, and the only way it'd be wrinkled is little d, little d. So if we do a Punnett square for that, we get big D, little d, big D, little d, big D, little d, and big D, little d. Now this here, this is the F1 generation. So now we have to take two of these guys and cross them. So if we do that, big D, little d, big D, little d, big D, big D, big D, little d, big D, little d, little d, little d. Okay, so we have smooth, 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 wrinkled here, based on our dominant and recessive calculations. Now that we got this information, it's basically, if we're talking about phenotypes, it's 3 smooth to 1 wrinkled. Let's put 1 wrinkled, okay? So that's our ratio here. It's supposed to be like a colon. All right, so 3 smooth to 1 wrinkled, or it's basically 75% smooth to 25% wrinkled. Okay? So knowing this is our F2 generation, because we took the F1s in order to make these guys, so this is our F2 generation. Now we could do our Punnett squares. Okay, so our null hypothesis. In a null hypothesis, we're going to say that the results will be no different than the expected 3-to-1 ratio. Okay, so that's our null hypothesis, that it's not going to be any different than what we expect, basically. So we have to calculate our expected. Here, this tells us what the outcome was. So we add those together. So 5,474 plus 1,850. We get 7,324. So this is our total. Now, if that's how many there is altogether, we want to calculate what we should expect based on our ratios. There's 3-to-1 ratio, so 75% should be smooth and 25% should be wrinkled. So we multiply that number by that. So 7,324 times 0.75 equals, and then 7,324 times 0.25 equals. So when we put it out, 0.75 times 7,324 gets us 5,493. This is smooth. And then for the wrinkled, 0.25 times 7,324 gets us 1,831 wrinkled. Okay. So these are our, right here, this is what we should expect if it is a 3-to-1 ratio. Now if you look at the numbers, you're like, okay, wow, that's pretty close and that's pretty close, but is that accepted? Are we actually looking at this actually happening? Is this close enough to our 3-to-1 ratio? Or is it so far off that we have to reject it and say that, okay, our null hypothesis is that it should be no different to this 3-to-1 ratio. Maybe there's a different mode of heredity being seen here. So here, when we say this 3-to-1 ratio, we're expecting that if it's complete dominance. But if complete dominance isn't happening here, or if there's gene linkage, then we wouldn't see that 3-to-1 ratio. So are these numbers close enough to this that it's accepted, or should we throw it out? So we do the chi-square test. So chi squared is the sum of, so the first one, observed minus expected. So the observed is 5,474 minus the expected, 5,493, and then we square that, divided by the expected, which is 5,493, plus, because we have, it's a sum total of, so plus the second thing we're looking at, we have 7,300, oops, my bad. We have the observed, which is 1,850, minus the expected 1,831 squared, divided by 1,831. So again, observed minus expected squared divided by expected. Okay, if we do this, let's go ahead and work this out. So we have 5,474 minus 5,493 equals, then we square that, and then divide it by the total, the expected 5,493, and we get 0.07. So this equals 0.07, plus we have to add that 2, and I like to round it to two significant figures here. Originally I got 0.065, then I just round it to 2 sig figs. Then this other one here, 1,850 minus 1,851. Oh, 31, my bad. That would definitely throw you off. Make sure you're careful with these. 1,850 minus 1,831 equals, square that, divided by 1,831. And I get 0.197, so I'm going to round that to 0.20. Okay? So if I add these two together, 0.7 plus 0.20, I get 0.27. Now I have to calculate my degrees of freedom. Degrees of freedom is the number of things I am comparing. So I'm comparing smooth and wrinkled, so I'm comparing two things. So 2 minus 1, so whatever the number of things you're comparing minus 1 equals 1 degree of freedom. Now, we need our little chart here to decide. So we have 1 degree of freedom, and we would have to reject our hypothesis of the expected 3-to-1 ratio based on complete dominance. We'd have to reject that if it was 3.84 or bigger on the numbers. We got 0.27. So since it's 0.27, our hypothesis is supported.